Hello guys, here's some of the molecular geometry that we're going to be doing today. Now your shape is going to depend on the valence electrons you have for each element that you're using. Let's go to example 1. Here you have a trigonal pyramidal, and if you notice it looks kind of like a little tent. Okay, your angle is 107 degrees between here and here. Okay, so when you have something like AS and something like hydrogen, remember that hydrogen has one valence electron and AS has one. Here, let's do them in a different color. 1, 2, 3, 4, 5 different valence electrons. So here, this is a covalent bond, and these are going to share. So in every bond, you have 2 electrons. So here, you need another hydrogen. So it can share with AS, and you need another hydrogen. Now that takes all of the unpaired valence electrons from AS, and now it has all 8 valence electrons. And hydrogen has shared its one, each one of them. But this shape is your trigonal pyramidal. Okay. Now this is your trigonal planar. Your trigonal planar looks kind of like a flat triangle or sometimes like a T. So if you have, let's say, another example would be, or let's do the one that's on top, boron has 1, 2, 3 valence electrons. Then hydrogen has 1. And because it's a covalent bond, it's going to share those valence electrons. This shape is your trigonal planar. You're going to use these to be able to match for your lab. Okay, this shape is a linear shape, and your degrees are 180 degrees. And if you notice, your electron negativity is going to go usually on the opposite direction. Okay, now because if it's an equal element, if you have the same one on the same side, on each side is going to have the same electron negativity force pulling on the opposite side, which means that you won't have anything moving because it's equal on both sides. So here, this is carbon dioxide. You have 2 oxygens pulling in the same force on the opposite direction. Here you have carbon. Therefore, this is going to be a non-polar bond because you have an equal pull to each side. Now here you have double bonds. Here you have oxygen. You have an equal pull. So these are non-polar bonds. Now, if you have something different like hydrogen and let's say a chlorine, you have a difference of electron negativity, that force, because one is going to be greater than the other. It's going to be pulling that hydrogen along. Because it's unequal, that is a polar bond. Okay, now all of these are examples of your linear shape. Okay, now here we have a water molecule, and your angle is 104.45 technically. So we usually round it off to 104.5. Now, this is how it looks in the model and your shape is bent or angular. Most of the time on a test you're going to see it as bent, but it can be both. Now this molecule is a tetrahedral. And again, because you have carbon and you have hydrogen and hydrogen in every single direction, you're going to have the same pool in every single direction. So this is a non-polar bond. Now this is a tetrahedral. Your angle here is 109.5 degrees. Okay, now what if I have, like down here, I still have carbon, I have a hydrogen, and a hydrogen, and a hydrogen. But here, instead of a hydrogen, this is a halogen. So it can be a chlorine or a bromine. This is going to actually have a stronger electron negativity force, and it's going to pull the hydrogen in the opposite direction. So because you do not have an equal pull, it's not equal. This is a polar bond. Okay, so now how are these shapes going to work? Well, it's going to work with your Lewis dot bonding. So carbon has 1, 2, 3, 4 valence electrons. And let's say we match that up with fluorine. Fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Fluorine already has 7. It's close to being stable and close to being happy. It's not going to give up any of its electrons. So carbon will say, well, fine, I'm going to share with you. And now fluorine has 8 valence electrons, but carbon now only has 3 available. So this fluorine is not going to do anything because now it's stable. So what can carbon do? It can attach itself to another fluorine. So let's make that just a little lower so we can have enough space to draw. So you can have 1, 2, 3, 4, 5, 6, 7 valence electrons. So these two will share. Now this fluorine has 8 and carbon only has 2 left. So we add another fluorine. And you're going to keep adding valence electrons, and I usually always leave the empty one closest to whether it's going to share or transfer valence electrons. Now because this is a covalent bond, remember that covalent bonds share valence electrons. Here we have another fluorine. 1, 2, 3, 4, 5, 6, 7. And this completes your molecule. So carbon has given up all of its 4, or shared all of its 4. And all of the fluorines now have 8 valence electrons, and so they are now stable. So your compound here is carbon F4, because it took 4 fluorines and 1 carbon to make this more stable. Now if you have an ionic bond, for example, let's say sodium has 1 valence electron, and let's go back to one of our halogens like bromine. Bromine has 1, 2, 3, 4, 5, 6, 7. Now for my Lewis dot structure, I always leave that empty space closer to the element. That way it's an easy bond. Ionic bonds transfer electrons. Now remember, if you have a nonmetal and a nonmetal, that's a covalent bond. If you have a metal and a nonmetal, that is an ionic bond. Okay, so here this dot will transfer into the empty space, and now you have 1 sodium and 1 bromine. because sodium gave up all of its electrons or transferred them, and bromine now has all 8. It is now stable. Okay, and that's it. This is a linear shape, and this one over here is a tetrahedral. And that's it.